going to do another one. You should remember from yesterday that dipole moment is expressed by the Greek letter mu and is equal to Q times R, where Q is the charge of the ions, which is really thought of as Q1 and Q2 because there's a cation and an anion. We don't really worry about the sign. We just multiply them. Most of the time, lots of times it's 1 times 1, so we don't even have to put it in the equation because it makes no difference. That's your dipole moment. And this R is the distance between the ions. Remember, we always have to think of this in terms of electrical charge. So we have our ions, basically we're talking about electrons. So we start with our electrical charge, the 1.6 times 10 to the negative 19th coulombs. And I have a distance up here in angstroms, so I also have to deal with that. I have to get from angstroms to meters. So I'm going to do my 1 times 10 to the negative 10th meters over an angstrom, because that's my equivalency factor. And then I was given a distance. This Q, let me make sure this is clear, this Q is this 1.6 times 10 to the negative 19th. Really out here, I would have like a 1 because H is a 1 plus, and F is a 1 minus, and 1 times 1 is 1. So that's why I don't put the Q there. I just use the electronic charge. Okay, so now I'm converting it, getting to meters from angstroms because I know my distance was given in meters and I need an answer in terms of debye, which is coulomb meters. So I put my R in, and then I have to use my second conversion factor, which is 1 debye is equal to 3.34 times 10 to the negative 30th coulomb meters. So I've gotten rid of coulombs, I've gotten rid of meters, I've gotten rid of angstroms, and I'm left with debye. So I can say that my dipole moment is equal to whatever that equals when I get my, oh, I gotta find a calculator. Punch that in and see what you get. I got 4.39 debye. Did you get that? Okay, I'm going to give you one more and I want to see if you can set it up. Let's say we have an no, I don't want that one. Let's do see calcium sulfide. Calculate dipole moment. If bond length is 1.28 angstroms, assume 100% ionic character is another way it could be phrased. Now see if you can set that up. Remember, you have to think about what are you dealing with in your compound? What are your ionic charges? Don't forget that part. It's really just repetition of what we just did, except for a change in charge. When you have an answer, stand up. Is your number a little larger than the last ones? It should be. Okay, find your lab partner or someone and check with them. Good job. What are your units on this? Divide. 24.5 was the correct answer. Raise your hand if you got it. Okay. These are not difficult. It's just remembering the pattern, remembering your conversions. Okay, so while we're talking about bond lengths and dipole moments, which all goes with bond length and bond strength, I want to talk a little bit more about that before we wrap this up. Okay, so first of all, bond length and bond strength go hand in hand. And the stability I'm going to say the stability of a molecule is related, seems pretty obvious, to its bond strength. And we think of this most when we're talking about molecules, when we're talking about covalent bonds. When we talk about ionic bonds, rather than the length of the bonds, I mean the length of the bonds comes into play, but what also comes into play is the number of bonds. So it should make sense to you in your brain at this point. As the number of bonds increases, what do you think happens to bond strength? What would you guess, Lucas? As the number of bonds between two atoms increases, like as I go from 1 to 3, what do you think happens to bond strength? It does go up. What made you think that? More bonds, more strong. Okay, so what about the more bonds makes it more strong? What's going on in there, in those little bonds? He says this. Yeah, they're being pulled together. Why? What do they want? They want a full outer shell. And they want to hold on to all those shared electrons so that they have their octet. So when you think ionic, when you're making like Lewis structure of an ionic compound, the more bonds, the more double bonds, the more triple bonds, the stronger the strength of the bond, and usually the shorter the length. It pulls the atoms together when they transfer those things. So when I'm thinking molecularly, we can actually measure what we call bond enthalpy. I don't know that we've had that word before. Anybody tell me what enthalpy is? Bond enthalpy? Okay, I didn't think we'd have that word. This is, think of this as the energy needed, or the energy change is probably a better way to say it, when 1 mole of bonds are broken in a substance. We speak of it in terms of moles instead of in terms of grams. Easy way to think of it, amount of energy needed to break a bond. So when I look at covalent bonds, I'm going to give you some examples. Let's say we have sulfur bonded to sulfur versus sulfur double bonded to sulfur. My bond enthalpy, and I'm going to give you this in kilojoules per mole. So how much energy it breaks it in kilojoules takes to break the bond in kilojoules per mole. This one takes 266 kilojoules per mole when I have one single bond. If I have a double bond, it takes 418. If I look at oxygen versus double bonded oxygen, this is 146, this is 495 kilojoules per mole. If I look at something not different like CO versus CO double bond, I've got 358 here and 798 here. So you can see in every single case, as I increase the number of double bonds, I'm increasing the bond enthalpy. Does that make sense? Can you see it? So as I add double bonds, my bond enthalpy goes up. It doesn't really matter if I'm talking about a diatomic molecule or if I'm talking about an actual molecular compound where I have two different things. So let's make a statement about that. Generally, as the number of bonds between atoms increases, the bond length decreases and the bond becomes stronger. This is true in both cases, ionic or covalent. We don't really talk about it in terms of metals. So this statement applies to both. The numbers I gave you dealt with covalent bonds. What Lucas and I discussed, we were talking about ionic bonds. All right, so I want to look at ionic bonds a little bit more. Ionic bond strength. See if you can remember this from early in the chapter. What form do ionic compounds take? What's their structure like? You even looked at it in lab. What? Crystalline. Okay. So we can say ionic bonds or ionic compounds would be better. Form, we called it a crystal lattice structure. The first crystal, which is the foundation of the whole structure, or the building block, however you want to think about it, is called the unit cell. We have that earlier in your notes, but just in case we need it. The whole thing the entire crystalline structure of the compound, do you remember what that's called? A crystal what? Anybody? Crystal lattice. So the foundation, the beginning is the unit cell. It builds crystal upon crystal until I get the final structure, which I call the crystal lattice. Now, every ionic compounds, or almost every, there are a couple amorphous ones, but almost every ionic compound forms a crystal lattice. If I want to separate it, then I need something called lattice energy. And that is equal to the energy required to completely separate 1 mole of a solid ionic compound. And we have a really simple formula to figure out lattice energy. We say E sub L, script L, is equal to K Q1 Q2 over D. And I'll tell you what those things mean. This is lattice energy. K is a constant. We've had it before. We're not even going to worry about K because it has no bearing on the lattice energy at all. It's a multiplicative. It makes it larger, but it doesn't change anything. We have to worry about our Q1. This is charge of first ion. Well, it's really charge of cation. Charge of cation. Q2 is the charge of the anion, and D is the separation distance. So basically, it's your cation times your anion divided by how far apart they are. This is the cation charge, this is the anion charge, this is the separation distance. So it breaks into something really fairly simple. It's multiplication and then division. We don't worry about charge up here. We just have to worry about the magnitude of the charge. Like, let's say I had AL N, and my D was equal to 0.76 angstroms. What's my charge on aluminum and nitride? What's the charge on aluminum, Evan? Do you know? 3+. Good. So this is 3+. Nitride's what, Jacob? 3-. So I have 3 times 3, so I have 9. 9 divided by 0.76 angstroms. I can leave it in angstroms unless you're given something else in the, don't pay attention to this, I don't know what I even put there. Whatever that works out to be. I would say that my is equal to 11.8. Those are pretty easy, and most of the time you don't really even have to do the math. You're given some kind of a comparison, so you really have to pay attention to your charges and how far apart they are. Obviously, if you're dividing by a bigger number, energy goes down, or a bigger distance between, your energy goes down. The magnitude of lattice energy, we can say that it depends on the size of the ions, size of the ion's charge, and arrangement. And when we say arrangement, we mean how far apart are they? Lattice energy increases as charge increases. And distance between ions decreases. So these kind of problems or questions, lots of times they'll show up in multiple choice, and they really don't require you to do any math. They really require you to think about charges and look at the numbers you're given for separation distance. I mean, you can plug them in if you want to, but you really don't need to. All right, very, very last thing, which I don't think we did before, and I want to make sure you have it. I think, and I want you to check this for me. In your notes, we talked about expanded octets, right? Did we talk about reduced octets at all? Okay, so I have one thing I want to show you. Less than an octet. This is pretty rare. More rare than the expansion. What two always have less than an octet? Yep. H and HE always. We also oftentimes see boron and beryllium. Okay, let's look at boron trifluoride, which would be BF3. Draw a Lewis structure for boron trifluoride. When you have it drawn, calculate your formal charge. When you have your formal charge calculated, stand up, and then we'll talk about it. Okay, if you have a formal charge of 0, stay standing. Oh, so close. Okay. Let's talk about this and see what you have. I want to know what yours looks like. Cole, how many electrons does boron have? 5. How about fluorine? How many do we have there? Total. Andrew? 21? Yeah. Okay, so I have 26 electrons to work with. Connor, did you have a 0 formal charge?
Yeah.
Tell me what you did.
I just single bonded all of them.
He single bonded all of them. That's how I would start. And then did you just fill in?
Yeah.
4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Did you put 2 down here? Yeah? Yeah. So, when I do that, let's look at my formal charge on my fluorines, because they're all the same, so I only need to do it once. Fluorine brought 7, and it has 2, 4, 6, 7, right. Boron brought 5, and it has 2, 3, 4, 5. Look at that, 0, 0, check. Now, does boron have a full outer shell? In this case? Yes? No? Yes. Yes. What? I don't understand your question, Marin. I didn't hear you, first of all. How many electrons does boron have in its outer shell, people? Look at your periodic table and figure it out. Its atomic number is 5, yes. How many electrons does it have in its outer shell? 3 or 5? I'm not going to tell you. I'm just waiting for you all to tell me. Do you agree with Marin or disagree? 3. Yeah? Okay. We better try this again. Thanks, Mayor. All right. So we have 3 plus 21, which should be 24. That is correct. If you had 24, that's what you should have. So I'm still going to do the same thing. Boron in the middle, FFF. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm out. Does boron have an octet? No, but let's check things out here. BF. Okay, 1, 2, 3. It brought 3. It has 3. Fluorine brought 7. 2, 4, 6, 7. Has 7. 0, 0. I have a good Lewis structure there, but boron doesn't have an octet. What happens if I want boron to have an octet, and let's say I take these two and I move them in? What happens to my formal charges? Now this one has 2, 4, 5, 6, so I have one of my fluorines that brought 7 and only has 6, so it has a 1 plus charge, and boron brought 3, and now it has 4, so it has a 1 minus charge. So I have a separation in charge. Is this an ion, a polyatomic ion? No, so I don't want any separation in charge, so this is not an ideal Lewis structure. That is why boron and beryllium both don't always have an octet, because when they have an octet, because of what they bring, the octet makes a big separation in the molecule, and when that separation exists, the molecule is less stable. So remember that if you get one on the test, that it can have less than 8. Boron, beryllium, of course hydrogen and helium. Well, you're never going to deal with helium, but hydrogen shows up a lot. Okay? Is that clear? Because I know we were a little off track back here. Watch your number of electrons that you start with. You'll have a periodic table. You can look, you can count. The other thing that, what else could come into play with boron? Why is it happy with maybe just 3? What's boron's electron configuration? One S2, 2S2, whoops, what the heck is that? 2S2, 2P1, is that right? Yeah. So that's how I get those 3 out there. I'd have to add 3 more. No. I'd have to add 5 to fill this up. I don't actually add 5. I'm really only adding 3. So you can look at this. Lots of times if we end in the 2s2p, we have room or have the ability to have less than an octet. Just like when you get to where you expand to 3D, you can have more than an octet. Yes, sir?
Why would this happen for any element that brings 3 valence electrons?
Why wouldn't this? Because after I move past, where's my little thing? After I move past my second period here, where boron and beryllium are, from here down I add the 3rd energy level, so I have 3D present. And because that 3D shows up, even though it's only may only have a couple of electrons in it, it allows for it to expand rather than contract. These guys up here, the reason that they don't have to have an octet, these two, or sometimes it'll show up a little farther down, but I just picked the 2 most common, is because of where they end in that 2nd energy level. So that's the logic behind expansion versus contraction of the octet. And I'm done talking. Aren't you happy? I hope you're having a good day, Jacob.